Hey everyone, today we're going to start looking at what are known as rational exponents, and I want to begin today's lesson by reviewing some of the properties of exponents that you've seen over the years. These are going to show up within a lot of the examples that we work through today. Okay, so let's say I have a raised to the power of m being multiplied by a raised to the power of n. So I have two expressions that have the same base a being multiplied together. So we know that this is going to simplify to a raised to the power of m plus n. You add the exponents in this case. Okay. Similarly, if we have a to the power of m divided by a to the power of n, our quotient property says we would subtract the exponents, and it would always be the numerator's exponent subtracted by the denominator's exponent. Okay. Let's say we have an expression a to the power of m that's being raised to another power, n. Here's where you would multiply the two powers together, a to the power of m times n. Okay. Let's say our expression has multiple parts, so we have ab as our expression, and it's being raised to the power of m. Well, then that means both a and b are in fact raised to that power. All right, and lastly, this is typically the one that we forget to apply the most often. If I have a being raised to a negative exponent, so in this case a to the power of negative m, I can make that into a positive exponent by putting it underneath a 1. Becomes 1 over a to the positive power of m. Okay, and that also works. Let's say we had 1 over a to the negative m. That is the same as a to the positive m over 1. Okay, so don't overcomplicate that. If you have a negative exponent, it can become positive by just moving it to the other half of the fraction. Okay. Now let's move forward and introduce the concept of a rational exponent to you. So a power that is known as a fraction, that's referred to as a rational exponent. If you recall, rational numbers are numbers that can be written as fractions of two integers. Okay. So here I have b raised to the rational exponent of m over n. This has an equivalent radical form associated with it. Okay, b to the power of m over n is the same as the nth root of b raised to the power of m. Okay, so notice where the numerator and the denominator from the rational exponent go when you put this into radical form. So the denominator becomes the index of your radical, right? The nth root here, and then the numerator becomes the power on the radicand. Okay, there is another equivalent form here that's sometimes useful to use. It would be equivalent to the nth root of b raised to the power of m. So the difference between the two radical forms here is just in the order in which you evaluate. So in the first one that I wrote out, I would raise b to the power of m first, and then I would find the nth root of it. In the second one that I just wrote out, I'd find the nth root of b first, then I would raise that result to the power of m. Okay. Now notice the stipulation that I have in red here. We always have to watch out for even roots. So when n, the denominator of the rational exponent, when n is even, then that means your base is going to have to be greater than or equal to 0 for all this to work. Otherwise, you have the potential of having a radicand that's negative. We know you can't have an even root of a negative number. It's not real. Okay? All right, so let's just practice moving back and forth between radical form and exponent form. Let's start on the left side here, write in radical form, x to the power of 1/4. That would just be the same as the fourth root of x to the first, which you don't have to write the power of 1. Okay? m raised to the 5/4 power, that would be the same as the 4th root of m to the 5th, or you could also say that's the 4th root of m raised to the 5th power. Okay. Next, on the right-hand side, we have radical form. We want to convert into exponent form. So the cube root of w squared, we're going to rewrite that as w raised to the power of 2/3. Remember, the index of the radical becomes the denominator of the rational exponent. And similarly, the 5th root of m to the 7th, that becomes m to the power of 7/5. Okay? So you just definitely got to make sure that you are able to rewrite back and forth between the two forms, because sometimes it's helpful to be in radical form, other times it's helpful to be in exponent form. Okay? All right, moving forward. Here we want to evaluate each expression, meaning just find the value of it, and if necessary, we're going to express our answer back in radical form, simplest radical form. Okay? So starting with the 4th root, or I'm sorry, 4 raised to the power of 3/2, that can be written as the square root of 4 cubed. Okay? Now, when I've written it that way, that means I actually have to do the cubing first. So this would become the square root of 4 cubed is 64. And then the square root of 64, we know, of course, is 8. Okay? Now, our other option, we could have, I'll do a different color here, we could have thought of this as the square root of 4, then raised to the 3rd power. And this would be the route that I would hope that you would take. It's just smaller numbers to work with here. We know the square root of 4 is just 2, right? And then 2 cubed would give us the 8 as well. So either approach works. Definitely what's in red, I think, is a little quicker, a little easier if you make that observation, because the numbers are just smaller that you have to calculate with. Okay? All right, next example in the middle, we have 49 being raised to the negative 1/2 power. So here's our first taste of a property of exponent needing applied. The fact that I have a negative exponent, that doesn't mean my answer is going to be negative. Okay? That's a very big misconception. Instead, that just means I should rewrite this as 1 over 49 to the positive 1/2 power. Then I'll go to radical form. 49 to the 1/2 power would just be the same as the square root of 49 to the 1st. Okay? And of course, we know that square root of 49 is 7. So notice this final answer. It's not negative. It's just a number smaller than 1. Okay? Next, we have 32 to the 2/5 power. So this will be kind of similar to the one that's over on the left here. I'm going to rewrite this as the 5th root of 32, and then I have a decision to make. Should I put the 2 on the inside or on the outside of the radical? Well, if you put it on the inside, then you're going to have to take 32 and square it, which that's going to be a pretty large number. And then that large number you're going to have to find the 5th root of. However, I'm noticing the 5th root of 32 is an integer, right? So I think it's going to be better to bring the power of 2 to the outside. So I know the 5th root of 32 is just 2, and then 2 squared simplifies me to 4. Okay? All right, let's move forward to a couple more examples here. Notice everything in example 2, all 3 of these, they simplified to where we didn't have a radical in the final answer. But I think you're going to see in these next few that's not going to be the case. Okay, So now I have 20 raised to the half power. So we know that that's the same as the square root of 20 raised to the first. Well, 20 is not a perfect square, right? So let's break it down. About 4 and 5, 2 and 2. There's a pair of 2's right there. So I can pull this out and pull a 2 out and say this simplifies to 2 times the square root of 5. Okay. Now I keep writing the index of 2 here. You don't always have to do that, right? We know if it's a square root, you don't have to write the index. All right, lastly, 4 raised to the 4th power, then raised to the 1/3 power. So here's where another property of exponents can come into play. We could multiply the power of 4 with the other power of 1/3. And that's going to make this 4 raised to the power of 4/3. Okay. Now I go to radical form, and I have one of two options. We could say the cube root of 4 raised to the 4th, or we could also said the cube root of 4 then raised to the 4th. Okay. Now in this particular case, I think it's more beneficial to account for the power of 4 first. Why? Well, the cube root of 4 doesn't simplify on its own. Okay? Cube root of 4 does not simplify on its own. So it's going to be better for me to go and raise that 4 to the 4th power. That becomes 256, right? Okay. And then I'm just going to break that down and try to simplify this radical. So 256 is actually a perfect square. It's 16 and 16. Then you've got, let's just go 4 and 4, 4 and 4. And I could break this down further, but I'm noticing right here's 3 4's that can be pulled out with 1 4 left over. So this is going to simplify to 4 times the cube root of 4. Done. Okay. So that's it for today as far as examples from me are concerned. Now you're going to move to practice 1. Try it yourself and then come back to the video, check your work.